groups that kind of behave together. So it kind of leads to the end of my talk, towards the end of the talk, and what I try to tell you is how powerful networks are for understanding the world that is around us. And there's a new science that has emerged that is actually called network science. You know, we are very proud of the fact that the national academies have written 2 different reports on that and how important it is. And the question is, what is network science? And network science is really an attempt to understand networks emerging in nature, technology, society, you name it, biology, and so on, using a unified set of tools and principles. And what is really new here is that despite the apparent differences between these networks, because think about it, I talked about social networks whose nodes are individuals. I talked about biological networks whose nodes are tiny molecules. I mentioned the World Wide Web whose nodes are web pages. Yet they are actually, the network itself has the same underlying structure. So these different networks are driven by the similar set of laws and mechanisms. And what I'd like to do in the next slide is to show you how much enthusiasm is about this science. And the way we do that, essentially, we don't have dollar bills essentially to show that, so I can't do what you did. I think that was wonderful. But we have something equivalent to the dollar bills. We have what we call citation. That is, if somebody publishes an important paper, then you can see how many other people have written papers that was based on that because they cited it in their paper. That's how we call citations. And network science is really at the end tail of a number of major discoveries in complexity science. And that's what I will try to illustrate here. So what you see is the years on the horizontal axis, and the vertical axis is citations. And let's think that those are each of them millions of dollars, okay? So that would kind of give us essentially a better idea of what we would put it in the same context that we had before. And I want you to focus essentially that, for example, at the purple curve. This is the paper that was published in 1963 that discovered chaos and the butterfly effect. Probably many of you have heard about it. It's a beautiful paper. It means that nobody really paid anything for it for about 10 years. Nobody cited it, nobody paid attention. And then about 75 people have discovered, oh, this is very interesting. And then more and more people started to write papers based on that. And these days it gets about 300 citations a year, which means that every year about 300 papers appear on the subject that think it's important enough to cite this paper. Many more appear on chaos, but there are about 300 of them cited. So it gives you an idea of the volume of that question. The other 2 curves correspond to 2 other major discoveries. One of them got the Nobel Prize and so on. They're already to chaos to a certain degree. This was 1960s, 70s. This was really the excitement in complexity. 1980s came fractals. And most of you probably have heard of the concept of fractals, these beautiful pictures. And the papers that appeared again were in the same market, you can see, because roughly they get the same number of citations, the same revenue if you want to think it as business terms. And but clearly created lots of excitement. I started out my professional life in this area essentially, and I wrote a number of papers. I contributed to those curves. Then came the end of 1990s and 2000, and network science came around. So what I'm going to show you is the 3 most cited papers in network science. I'm happy to say that 2 of them come from my group, and you can kind of compare how they actually look compared to these other truly important areas. So we think that we're part of a growth industry here, if you want to think of those terms. So truly this is kind of capturing the excitement that is happening. And the question is, why is it? Why is it happening at a completely different scale? Why is it that a huge number of scientists are really taking network science is really their science? And the reason for that, I think that is my interpretation, is because lots of fields have looked at it and said, this is us. Computer scientists say, well, networks, I mean, come on, we are internet and World Wide Web. I mean, you're not telling us anything new. But the social scientists say, well, we invented social networks for 40 years. This is really us, so we are part of it. And the biologists come along and say, we need to understand cancer. And cancer is not a single gene disease. It's really coming from the interactions of many, many different genes. And we need to have the roadmap of how these molecules connect to each other and how these genes. So network science is us, and they have really invested hundreds of millions of dollars of mapping out their cells. And eventually will also come the economists who will say, if we want to understand the economy, we have to think of cancer. We're not there yet. I mean, of networks, we're not there yet, but we think it's going to happen. So I think this kind of the fact that people have really considered this is really them that explains these curves. But what really excites me on the intellectual level, however, is the fact that you have these completely different networks that have nothing to do with each other, and they share the same underlying topology. And from my physicist perspective, this is beautiful. This is what we call universality. The fact that completely different systems converge essentially to the same architecture. And understanding why this happens and what are the consequences of that is really a very beautiful exercise. So I could end here, or I can tell you why Kevin Bacon. All right. 2 more slides. Okay. So why Kevin Bacon? So Kevin Bacon is certainly a very prominent actor, and he had made more than 46 movies. Actually, probably does much more now, more like 60 now. It played together with 1,800 actors, and every separation to any other actors is 2.79. That is, typically on average, you can connect him to any actor between 2 to 3 links. So that's why it's so easy to link him to everybody else. But is he the most connected one? Well, we did a list. This was not the first list we did. First we said, well, probably the actors who made the most movies would be the most connected one. And Kevin Bacon must be among them. So we did the first list. And we got these very strange names. We could not recognize any of them. And we started to look, who are these people, So, and then we realized that with one exception, they were all porno stars. That exception was actually the voice of one of the very famous cartoon characters whom I remember, actually. So then we said, let's take some other route, because obviously this is not. And then we started to say, what's the average distance between an actor and anybody else? That is, how easy to connect one actor to all the other actors. And when we listed that, it turned out that number 1 was not Kevin Bacon, but it was Rod Steiger. Probably many of you know him. The second one was Donald Pleasance. Number 3, Martin Sheen. You probably know the president and so on. And we then down, in the first 10 lists, there was no Kevin Bacon. Then we looked at the first 100 list, and there was no Kevin Bacon. And then the first 250, and there was no Kevin Bacon. And eventually, we found him in the position of 876. So, if you were to look at the Hollywood as a network, really, then Rod Steiger would be a big hub, Donald Pleasance, Martin Sheen, and then if you have a magnifying glass, it would actually be bigger down there. Thank you very much for your attention.